basic probabilities. So some of you might understand all of these ideas. Oh, it doesn't have a blank back side, sorry. Some of you might understand all of these ideas, and they're not really that new to you. So this is not in the packet I gave you yesterday. The probability stats packet online is now bigger than it was originally if you printed it out. I know, I'm so sorry, okay? So here is what I am telling you. Okay, multiple options for those of you that are stressing out. Okay, so option 1, if you feel the need to write everything down, I would just write down the key terms because the pictures you see are straight from the textbook. You have that resource, okay? And I would just number the examples and write the answer or whatever work you want with them and not worry about copying them down and print it out when you get home tonight. Does that work for you? Okay. Option 2. This might not be any different than what you've seen before, so you might not really need to write a lot of this down. You might just have to talk with your group and work out some problems and make sure that you're good with understanding. Okay? Option 3 would be to copy everything down, but I don't think you'll learn anything if you're trying to copy everything that fast. Okay? So you can just transfer it. Are we okay with that? All right. So we're going to calculate 2 probabilities today, experimental and theoretical. Okay? So experimental probability is based on what? An experiment, okay? So, for example, what would you guys say is the probability if I pulled out a quarter and I want to flip a heads? What's the probability of me getting a heads when I flip the coin? 50% or 1/2, okay? Now, if I flip a coin 100 times as an experiment, is my experimental probability of getting a heads necessarily going to be exactly 1/2? No. The theoretical probability is we know all the possible outcomes. This is how many of them are favorable for you. So this is how it should work out, right? But how it should work out, I mean, people still go to Las Vegas, right? And they still gamble and do these kinds of things, even though it should work out a certain way, okay? Because sometimes it works out differently, right? And so you feel like you have a chance. So I could flip that coin 100 times and maybe get 40 heads. My experimental probability then of getting a heads would be 40 out of 100, okay? Which is like 4 out of 10 or 2 out of 5. That's not 1/2. But that's because I based it on my experiment and not on theory, okay? So here, if you had 119 animals at the zoo and 19 of them have wings, what is the experimental probability that any animal at the zoo has wings? Anybody? Kenny? 19 out of 119. Okay? That's it. All it does is take the data straight from your experiment. Okay? Does anybody know what the probability would be that something did not have wings? Samantha? So she says 100 out of 19. Do you guys know where she's getting that from? 119 is in total, right? So when you say something that has to happen or either not happen, like the animal has wings, okay? If I talk about the probability of it having wings versus the probability of it not having wings, what's true about those 2 separate probabilities? Michelle? They add up to 100% or 1 in total because either the animal has wings or it doesn't, which means every animal has to fall into one category, right? So those 2 things together should add up to the complete set, 100% or 1, if we're looking at the fraction. Okay? Those things are called complements of each other. Okay? Wings, not wings. All right, so vocab. We just talked about the theoretical probability. It means without an experiment, you're just saying, here's what I know could happen. Here's how many times it should happen like that. Here's the probability of it happening. And then, so that's the official definition. So notation that you might see. You might see a P and then something written inside of here. This says A, but A is like an event. So somebody could write P and then in the parentheses write tossing a coin and getting heads. Getting heads on a coin toss. That's what A could say. All right? All the probabilities have to fall between 0 and 1. Somebody explain that statement. What does that mean? All probabilities are greater than or equal to 0 or less than or equal to 1. Good. The percentage, if you think about it like that, has to be between 0 and 100%. Okay? What if the probability is 0? What does that mean about the event that you're speaking of? Ashley? It can't happen. And if the probability is 1, Lauren? It's certain to happen. Okay? All right. If we put the line over it, okay, that means the probability that event A will not happen. So like for the bird thing that we just, or not bird, I said bird because we were talking about wings, okay? The probability we just calculated experimentally, you calculated the probability that the animal has wings, right? And you came up with 19 out of 119. Fair enough. If I had gone like this, what would I be asking you to calculate now? Andrew? Good. Okay, basically the complement of that. This category was has wings. This is the other option, okay, which is it doesn't have wings. And notice how they say you could calculate it. 1 minus what you were saying before, which Samantha already told us, turns out to be this. The reason 1 minus that is what we talked about. It had wings or it didn't have wings. So if we added all of that up, we should have 100% of the population or the 1 in total. Okay, so each category makes up their part of that 100% or that 1. Okay? All right. So what's the theoretical probability of each event in example 2? A, getting a number less than 3 on one roll of a fair number cube. So like a die. Kenny. Okay, so Kenny says 1/3. Are you guys with that? So to get less than 3, what are your options? What can you get? 1 or 2 or that's it, right? So 1 or 2 because it specifically said less than 3. So 2 outcomes are favorable to me. How many outcomes are there possible on the die in total? 6, right? I could roll a 1, a 2, a 3, a 4, a 5, or a 6. Okay. So what about part B? Getting a sum that is a multiple of 4 on one roll of 2 fair number cubes. So you're rolling 2 dice at a time. So when you print out your packet, there's actually a reference chart in there for those of you that aren't familiar with dice and cards and things like that because they come up in probability a lot. When you roll 2 dice, okay, here's 1, here's the other. I could roll a 1 and a 1, and that sum would be 2. I could roll a 1 and a 2, and the sum would be 3. Okay, and so this kind of thing continues. Like this. So this is all of the possible outcomes. Okay? And notice, like 11 could be a 6 on this die and a 5 on this die, or a 5 on the first die but a 6 on the second die. Those are 2 different outcomes because the individual die is showing something different. So for it, that is a different roll, so we would count it that many times. So to get a sum that is a multiple of 4 on one roll of 2 of these number cubes. So first of all, how many sums are there in total? What are the total possible number of outcomes when you roll the 2 dice and you're looking at the sum? So this is a 6 by 6 chart. So there's 36 different outcomes, right? And yes, I get it. 3 is 2 and 1, and it's 1 and 2. But again, those are different because there's different die showing different numbers. Think about them being different colors, like if this one was green and this one was red. And that helps you understand why you have to count a 2 and on this one different than if you had gotten the 2 on this one. Okay? So there's 36 possibilities, okay, for my sum. How many of them meet the criteria, which is being a multiple of 4? So 4, 8, and 12, okay, would be the multiples of 4. So 5, 8, 9 of them meet that criteria. Okay. So 1/4 is the probability, or a 25% chance of that happening. Okay. All right, and so then example 3 says, what is the theoretical probability of being dealt exactly 3/8 in a 5-card hand from a standard 52-card deck? So go ahead with your group for a minute and think about how bottom of the probability calculation, just the total number of things, of possibilities, okay? So you're being dealt a 5-card hand. How many different ways can you be dealt a 5-card hand? A lot. Okay. And let me ask you this. Let's say the person deals your cards and they come in this order. 2, 3, 4, 5, 6. So your cards say 2, 3, 4, 5, 6. Okay. Now let's say the next deal you happen to get the same cards, but they were 6, 5, 2, 3, 4. Do you have the same hand that you had the time before? Yes. Okay, because a hand is a group of cards, right? It doesn't, I can move them in my hand, right, and no one knows. Okay, like think about when you're playing Go Fish. Does it matter if you got the 2 first, second, or third when you were dealt the original hand? No. You can move it where you want to order them how you want, right, but it's part of that group, okay? So basically when I ask you how many 5-card hands are there, I want to know how many different ways can you make groups of 5 cards from your 52-card deck? Andrew. How did you get that? Good. Okay, so he did this. So remember yesterday, our purpose in learning the permutations and combinations was because when we got to places where things were difficult to count, like ways to group objects, they provided us with a tool. Why a combination and not a permutation? Because 2, 3, 4, 5, 6 is the same as 6, 3, 2, 4, 5, right? It's the same group of cards that I'm holding in my hand. So order doesn't matter, okay? So this is the total number of ways that you can pick 5 cards from a 52-card deck. Now the question becomes, how many ways are there to have exactly 3/8 in your hand? Okay. So, can you have different groups of 3/8? Yeah, because I could have an 8 of diamonds and spades and hearts, or I could have clubs and spades and diamonds, right? So there are multiple groups of 3/8. We could probably count the multiple groups of 3/8, right? So you could have like hearts, diamonds, clubs, hearts, diamonds, spades, hearts, clubs, spades. What could I do instead of writing out all of these things? I can't do factorial because of the order. That's the issue. I had to think about it for a minute, I know. I can't do factorial because of the order, because I'm not going to count this again like this, right? Because I don't matter if I had hearts, then diamonds, then clubs, or hearts and clubs and diamonds. They're still the same group. So I'm not going to... Okay, say it again, Ben. The C, okay, combinations, right? And what am I calculating the combination of here? I'm choosing 3, clearly, right? Out of how many? 4. Okay, because there's 4 kinds of 8s in the deck, and I want to count the number of ways to choose 3 of them. But that's not the total calculation on how to get the hand, because how many cards are in my hand in total? 5. So this is like making that tree again, right? What I've done is I've just counted all the ways I could arrange the 8s, right? But now that I've arranged the 8s, from there, I need to, these 8s could be paired with, and I need to count all of the ways that they could be paired with any two other cards from the deck. Can 8 be included in it? No, but I could have like an ace and a king. Oh, but this could be like, I could have the ace of hearts and the king of hearts, or I could have the ace of diamonds and the king of diamonds. How am I going to, okay, so we clearly don't want to write it out, right? Even though it's only a group of 2, it's going to be a phenomenally long list. How could I calculate how many things will be in that list without writing them out? Kenny? Another combination, okay. So this calculation is going to be another combination. How many are we choosing at a time? 2. Out of how many options? 48. Very good. Why 48 and not 52? Because I can't include the 8s, right? So this counted the 8s. This counted the other 2 things the 8s could be paired with. So remember what that means. The top of my tree has this many branches, whatever that comes out to be, right? Each one of those branches has this many branches coming off of it. Okay? So how do I calculate my total number of options? Is this how many ways to pick the 8s, and this is how many ways to pick the 2 other cards? I multiply them. So the top of this probability is going to look like this. Okay? So think about how you guys figured this out. We knew we couldn't do that because it wasn't just like a very finite set that was super easy to count. It was like ways to group things, right? So the minute that we found out we were trying to group things, we knew we could use combinations or permutations. We chose combinations because the order didn't matter, okay? This was the same hand as this. So combinations counted it. This counted, I'm picking 5 cards from 52. This said, well, how many ways can I pick the 8s? How many ways can I pick the other cards? Any of these can be paired with any of these, and it's going to make this astronomical amount of possibilities. Okay, and so those get multiplied together. Okay? So we can do this as a decimal, and we can see what this turns out to be. So remember, in your math button, it has buttons for the combination. Oh, except for I did a bad thing. Probability of that happening is 0.0017, okay? Or in other words, a 0.17% chance, okay? So any of you that have played like poker or something like that with your family for fun, you know that getting dealt like 3 of a kind is kind of a big like, oh, I have a good hand. I would definitely play this hand and think I could beat somebody. The reason why it's so believable that you have a good hand and you could probably beat somebody is the odds of that happening are this. Now, this was specifically for 3 8s. If you then said 3 of a kind for anything, okay? It's okay, don't get a headache. All right. If this is just for 3 8s, right? If I wanted 3 of a kind of anything, what could I do to that probability to make it show it was for anything and not just for 8s? Kenny? Multiply by, and then let me just check your 11. So we would want to count it. Okay, I can do it not only for 8s, but this same the calculation would be the same, right? It wouldn't be any different for 8s or 2s or aces or anything like that. So if this is the calculation for 8s, I could multiply it. So ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So there's 13 different types of cards, right? So I would multiply it by 13. Okay. No, because I want to include 8 also. Yeah. Okay, yeah. So I wouldn't multiply it by 12 because remember, if I multiply it by 1, am I going to get anything different than what I have? No. If I multiply it by 2, it is counting this twice. So what's the chance you get an 8 or a 9? Something like that. So I would multiply by 13 to include all possibilities. Okay? So no, not, in this case I'm not taking anything away, but probability as a definition, okay, says how many ways do you get what you want divided by how many things could happen in total. Okay? All right, so in your groups, we're going to skip example 4, but go ahead and go to example 5 and see if you can calculate these. All right, so number 1, okay, paradise is rolled, one's green, one's red. Find the probabilities of the following. Who can tell us what's the probability that you get a total of 2? Michelle. Good, 1 out of 36. Oops. Looking at these outcomes here, there's only one way to get to a 1 on each die. Okay? Now, in that case, we don't say like, oh, but what if the dice switched the numbers because they both had a 1 on them? So if they switched, they would still both have a 1 on them. Okay? So that's why those double things only turn out once in the chart. Okay. 2, the total is 10. Sean. 1/12, okay? So you'll see 3 totals of 10 up there out of 36, which is 1/12. Good. All right. What about number 3? The total is at least 10. Yeah, 10. 1/6. So, good. All right. So there's 6 things up there that are 10 or more, right? At least 10 out of 36 possibilities total. So 1/6. Okay. Number 4, the total is at most 10. Savannah? Good. These are the only ones we wouldn't include. So 33 out of 36, those can be reduced by 3, so 11 out of 12. Okay. Number 5, the numbers on the die are 2 and 7. Impossible. Good. So the probability of that happening is 0. Dice are 6-sided. Sorry. If it makes you guys feel any better, I wrote it, and then one year when I was making the answer key for it, I answered it with a number. And then went, what the heck? And fixed it real quick. But, yeah. We get so wrapped up in doing the math, we forget, like, to think about real stuff. All right. What would be the chances that the green die is 2 and the red die is 5? Good, 1 out of 36. Because you can't choose a 5 here and a 2 here as well as a 2 here and a 5 here. It's like this one had to be the 5 and then this one had to be the 2. It's that one outcome out of the chart of 36. Okay? All right, and what about number 7? If the green die was 2 or the red die was 5? Sean? 1/3? Okay, so green die was 2, so let's say this one's the green, whatever. All of these outcomes had the green die being 2, right? And then, what's the other one? 5. Outcomes have the red die being 5. So that is, it looks like 6 plus 6, which is 12. However, what did we do here? Yeah, there's an intersection. Can I count that twice? No. So basically, the way I'm calculating it is like, yeah, there were 6 for that and there were 6 for that, but one of them I accidentally counted twice. Okay? That's how I'm getting how many out of 36 meet this criteria. So it's going to end up being 11 out of 36. Okay? And you're going to see later that idea is important. Whenever they say or, we have like more options, so we get to add together some of these options and possibilities, but we have to be super careful that when they overlap, we don't count that in each category and count it as an extra possibility. Okay? All right, so basically, this is what probability is about.